In this episode, we're going to take a topic that can feel intimidating, bias in automated decisions and analytics, and make it practical enough that you can reason through real scenarios with calm structure. Beginners often hear bias and immediately think of obvious prejudice, but in technology systems, bias can be subtle, mathematical, and accidental, and it can still create serious harm when systems make or influence decisions about people. For the Certified Information Privacy Technologist, CIPT, exam, you are not expected to be a data scientist, but you are expected to recognize where automated decisions can go wrong, why that matters for privacy and trust, and what kinds of controls reduce the risk. Automated decisions and analytics can affect who gets opportunities, who gets flagged as risky, who sees certain content, and who gets extra scrutiny, and those impacts can compound over time. Bias mitigation is not a one-time fix, because models drift, data changes, and the world changes. So sustainable mitigation means building processes and checks that continue to work as the system evolves. By the end, you should understand the main sources of bias, how bias shows up in data-driven systems, and what a privacy technologist can recommend that is practical and scalable. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful place to start is to understand why bias is a privacy issue and not only a fairness issue, because privacy harms often include being categorized, profiled, or treated differently based on data-derived conclusions. When an organization collects data and uses it to infer traits, segment users, or predict behavior, it is shaping people's experiences and opportunities, and those inferences can be wrong or unfair. Bias can also change what data is collected, because systems often intensify observation of certain groups, which creates a feedback loop where those groups are monitored more, flagged more, and then used as evidence that more monitoring is needed. That loop is both a fairness problem and a privacy problem because it increases surveillance and reduces autonomy for some people more than others. From a trust standpoint, bias undermines the legitimacy of data processing because users may feel the organization is not simply using data to provide service, but using data to judge them without transparency or recourse. In many regulatory and ethical environments, profiling and automated decision-making also carry special obligations, which means bias becomes a compliance risk as well as a harm risk. The exam can test this by presenting a profiling scenario and asking what control best reduces risk, and the best answer often includes both technical and governance measures. Bias in automated systems usually has multiple sources, and the first big source is data, because models learn from the patterns you feed them. If your training data reflects historical inequities, the model can reproduce those inequities even if you never include explicit sensitive attributes. If your data is incomplete, such as missing information for certain populations, the model may be less accurate for those groups and may produce higher error rates. If your data is collected through a biased process, such as collecting more data on some users than others due to business practices, then the model is trained on an uneven picture of reality. In analytics, bias can also come from selection bias, where the data you have represents only those who were measured, which can exclude people who avoided the system or were excluded by design. Beginners sometimes assume data is objective because it is stored in a database, but data is produced by processes, and processes have assumptions. A privacy technologist doesn't need to tune models, but they do need to ask where the data came from, who is missing, and what hidden proxies might be present. That line of questioning is high yield because many bias problems start long before any model is trained. A second major source of bias is measurement and labeling, because models learn not only from raw inputs, but from the outcomes you define and the labels you assign. If you label an outcome in a way that is influenced by human judgment, such as labeling someone as suspicious based on subjective reports, then the model can learn the biases of the labelers rather than the reality of risk. If your measurement tools are uneven, such as sensors that perform differently on different groups or forms that capture information inconsistently, then the data you feed into analytics will contain systematic errors. Even the definition of success can introduce bias, because a model optimized for a business metric like conversion can produce unfair outcomes if it rewards targeting certain groups more aggressively. In privacy terms, this matters because people may be categorized and treated based on flawed measurements, and those categories can become sticky in a system, influencing future decisions. A privacy technologist can advise teams to examine how labels are created, whether outcomes are defined fairly, and whether measurement errors might concentrate on certain populations. They can also recommend governance steps like review of labeling guidelines and audits of measurement quality. On the exam, being able to spot biased labeling as a root cause can help you choose mitigation actions that address the system's foundation rather than only its surface. A third source of bias is feature selection and proxy variables, which is where systems appear neutral while still producing discriminatory patterns. A proxy is a variable that correlates with a sensitive trait, such as using zip code as a proxy for socioeconomic status or race in some contexts. Another proxy might be device type, browsing behavior, or network attributes that correlate with demographic factors. Models can use proxies to make decisions that have disparate impact even if the model never sees a sensitive attribute directly. This is particularly relevant to privacy because the more data you collect, the more proxy pathways you create, which increases the ability to infer sensitive traits unintentionally or intentionally. Minimization helps here because collecting less reduces the proxy surface area, but minimization must be thoughtful because removing one variable might cause the model to rely more heavily on another proxy. A privacy technologist can advise teams to examine features for proxy risk, to test outcomes across groups where feasible, and to avoid features that create high-sensitivity inference risk without clear necessity. This aligns with contextual integrity thinking, because using proxies to infer sensitive traits can violate user expectations even if the inputs seemed ordinary. Exam questions that involve segmentation or profiling often hide proxy risk in the scenario, and recognizing it is a key skill. Bias also emerges from how decisions are applied, not just how models are trained, because implementation choices can amplify unfairness. For example, a model output might be a score, but the system might convert that score into a hard decision with a strict threshold that affects some users more than others. Another system might use a score to allocate resources, like support attention or fraud review, and that allocation can create unequal treatment if the model has different error rates across groups. Bias can also appear in feedback loops, where a system's decisions influence future data, like when a model flags certain users more often, leading to more data collection about them, which then reinforces the model's belief that they are risky. In privacy terms, this can mean certain groups are subject to greater observation, greater friction, or greater restriction, which can be experienced as both unfair and invasive. Mitigation often involves evaluating not only model accuracy, but also downstream effects, including how decisions impact user experience and what recourse exists. A privacy technologist can recommend that automated decisions include human review for high-impact outcomes, that thresholds be evaluated for disparate impact, and that monitoring detect feedback loops. The exam rewards thinking that considers system behavior over time rather than treating model outputs as static truth. Another important part of bias mitigation is recognizing that bias is not only about protected characteristics, but also about context and vulnerability. Systems can disadvantage people who have less stable internet access, less familiarity with technology, or fewer resources, even if the system is not targeting them. For example, an authentication system that relies heavily on smartphone access can disadvantage people without reliable devices, and an analytics system that interprets lack of engagement as lack of interest can misrepresent people who are cautious about tracking. These issues can translate into privacy harms because vulnerable users may be forced into sharing more data to get access or may be denied opportunities because the system interprets their behavior incorrectly. Ethical design choices like providing alternatives, limiting unnecessary tracking, and avoiding punitive assumptions can reduce these harms. In a privacy program, it is also important to consider accessibility and usability as part of fairness, because choices that are hard to exercise can disproportionately burden some users. The exam can test this through scenarios where a neutral design produces uneven outcomes, and the best answer often includes designing for inclusion and meaningful control. Mitigation strategies need to be organized so you can pick the right one for the scenario. And a helpful way is to think in 3 layers: data layer, model layer, and decision layer. At the data layer, mitigation can include improving data quality, reducing missingness, ensuring representative sampling, and limiting unnecessary collection that creates proxy risks. At the model layer, mitigation can include testing for disparate error rates, adjusting training approaches, and validating that the model behaves reasonably across relevant groups. At the decision layer, mitigation can include adjusting thresholds, adding human review for high-impact cases, providing explanations and appeals, and monitoring for feedback loops and drift. A privacy technologist might not implement these changes directly, but they can advise which layer is most likely driving the harm and what type of control is needed. Beginners sometimes jump straight to adding more data to improve accuracy, but more data can increase privacy risk and can deepen proxy issues. So the better approach is to evaluate whether the problem is data quality, label quality, or decision application. On the exam, the best answer often identifies the correct layer and proposes a mitigation that is plausible and effective. This is also where structured risk thinking helps, because you prioritize mitigations that reduce the most harm. Transparency and explainability are also part of bias mitigation, because people need to understand when they are subject to automated decisions and what that means for them. Explainability does not always mean revealing the full internal model, but it does mean providing understandable reasons and pathways for recourse, especially when decisions have significant impact. Without transparency, users may experience automated decisions as arbitrary and discriminatory, and they may have no way to correct errors, which increases harm and erodes trust. From a privacy standpoint, transparency also helps users understand what data is being used and how it influences outcomes, which supports informed participation and meaningful choice. A privacy technologist can advise teams to disclose when automation is used, to provide user-friendly explanations, and to design appeal mechanisms that are not hostile or burdensome. They can also advise that explanations should not reveal sensitive information about other users or about system security, because transparency must be balanced with protection. Exam scenarios often include user complaints about unfair treatment, and the best answer frequently includes improving transparency and recourse alongside technical mitigation. Bias mitigation also depends on strong monitoring and governance, because models and analytics systems drift as the world changes. Even if a model is tested carefully before launch, changes in user behavior, changes in data collection, and changes in external conditions can alter outcomes. Monitoring means tracking performance, error rates, and outcome distributions over time, and it should include checks for disparate impact where feasible. Governance means defining who is accountable for monitoring, what thresholds trigger investigation, and what actions are taken when bias signals appear. It also means maintaining documentation of how the model was built, what data was used, what tests were performed, and what limitations are known, because accountability depends on evidence. A privacy technologist can push for these governance elements because they make ethical commitments enforceable. This ties back to the idea of sustainable scale, because without monitoring and accountability, bias mitigation becomes a one-time promise that slowly erodes. On the exam, answers that include ongoing monitoring and clear ownership often reflect maturity because they acknowledge drift and long-term risk. Another key mitigation is minimization and purpose discipline, because automated analytics often expand beyond the original purpose in ways that increase both bias risk and privacy risk. When data collected for service delivery is reused for profiling or eligibility decisions, the context changes, and both fairness expectations and privacy expectations can be violated. Purpose discipline helps by ensuring that high-impact decisions are not quietly powered by data that users never expected to influence outcomes. Minimization helps by reducing the amount of behavioral and contextual data available for proxy inference, which can reduce unintended discrimination. This is not an argument against analytics, but an argument for careful scope. If an analytics feature is optional and not essential, it should not be quietly used to make consequential decisions about people. A privacy technologist can advise teams to separate data used for core operations from data used for experimentation, to limit use of sensitive inferences, and to require review before expanding analytics into decision-making. Exam questions that involve repurposing data for new decisions often reward answers that restrict scope and require review, because that reflects a privacy-respecting approach. To keep this exam ready, you can practice a calm reasoning routine that works whenever a scenario involves automated decisions, scoring, or profiling. Start by identifying what decision is being influenced and how consequential it is, because higher impact requires stronger controls. Then identify what data is being used and ask whether it could contain proxies or reflect uneven collection or labeling. Next, consider whether the system's output is being applied in a way that could create disparate impact, such as strict thresholds or resource allocation rules. Then identify what recourse exists for users, including transparency, explanation, and appeal, because lack of recourse turns errors into persistent harm. After that, consider monitoring and governance, asking who owns ongoing evaluation and how drift is detected. Finally, identify mitigations that match the root cause layer, whether it's data quality, model behavior, or decision application, and prioritize those that reduce harm while respecting minimization. This routine helps you avoid vague answers like improve fairness and instead choose concrete actions that can be implemented. It also aligns with what the CIPT exam tends to reward, which is structured judgment that connects ethics to operational controls. When you can mitigate bias in automated decisions and analytics, you protect people from unfair treatment and you strengthen the legitimacy of data-driven systems, which is a central part of building user trust. For the Certified Information Privacy Technologist (CIPT) exam, this topic matters because it tests integrated thinking across data collection, purpose, transparency, and governance, not just technical knowledge. Bias can emerge from data gaps, biased labels, proxy variables, decision thresholds, and feedback loops, and effective mitigation requires choosing controls that match the real driver of harm. A privacy technologist's role is often to ask the right questions, insist on accountability, and help teams design for meaningful transparency and recourse, while also advocating for minimization and purpose discipline. If you can apply the three-layer view of data, model, and decision, and pair it with monitoring and governance that persists over time, you'll be able to reason through complex scenarios without panic. That's the skill the exam rewards, and it's also the skill that makes ethical, privacy-respecting automation possible at real-world scale.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.